As you learned earlier, for a body of mass m attached to the end of a spring executing simple harmonic motion with amplitude a, its displacement as a function of time t is denoted as x is equal to a cos omega t, and its velocity as function of time t is denoted as v is equal to minus a omega sin omega t. For simplicity, consider the initial phases as 0. The kinetic energy of a body executing simple harmonic motion can be written as Ke at time t is equal to half mv square. Substituting the value of v, we get the expression for kinetic energy as half m into a square omega square sin square omega t. Let this be equation 1. As you know, the value of spring constant K is equal to m omega square. By replacing m omega square by K in equation 1, we get half K a square sin square omega t. Let this be equation 2. As the displacement of the body in simple harmonic motion is x is equal to a cos omega t, we can write cos omega t is equal to x by a. Therefore, sin omega t can be written as square root 1 minus cos square omega t. On substitution, we get sin omega t is equal to under root 1 minus x square by a square, which is equal to under root a square minus x square by a square, or sin square omega t is equal to a square minus x square by a square. Substituting the value of sin square omega t in equation 1 and simplifying, we get kinetic energy Ke at time t is equal to half m omega square into a square minus x square. Let this be equation 3. From equation 3, we see that kinetic energy is maximum when displacement x is equal to 0. Thus, maximum kinetic energy is equal to half m omega square into a square, or half k a square. Let this be equation 4. We also see that kinetic energy is 0 when displacement x is equal to amplitude a. Now, let us write the expression for potential energy. As you know, the spring force F is equal to minus kx is a conservative force. As discussed earlier, when a body executing oscillatory motion is under the action of such a force, the potential energy of the particle u of t can be written as half kx square, where k is the spring constant and x is the displacement of the body from the mean position at time t. Let this be equation 5. Substituting x equal to a cos omega t in equation 5, we can write the potential energy as u of t is equal to half k a square cos square omega t. Let this be equation 6. Potential energy is maximum when displacement x is maximum. That is, x is equal to amplitude a. Maximum potential energy is equal to half k a square. When x is equal to 0, that is, the body is at the mean position, potential energy is 0. Now let us write the expression for total mechanical energy of the body in simple harmonic motion. Total mechanical energy of the body in simple harmonic motion is equal to the sum of its kinetic energy and potential energy for any position. Substituting the expressions for kinetic energy and potential energy and simplifying, we get total mechanical energy is equal to half k a square. Let this be equation 7. We see that maximum kinetic energy and maximum potential energy are equal to the total mechanical energy. Total mechanical energy is independent of position and time t. When a body in simple harmonic motion oscillates with a time period t, then the variation in its kinetic and potential energy with time t is shown by the graphs for kinetic energy and potential energy. We can see that the graph of kinetic energy repeats after every half of the time period t. It's the same with potential energy as shown in the graph. But we see that the total energy remains constant. The kinetic energy and potential energy of a body in simple harmonic motion are always positive. As the body moves from the mean to the extreme, its kinetic energy decreases and potential energy increases. When it moves from the extreme to the mean, its kinetic energy increases and potential energy decreases. Consider a spring executing oscillatory motion. When a body attached to a spring executes oscillatory motion, it is under the action of a variable force known as spring force. The spring force is the restoring force that is responsible for bringing the body back to its mean position. Spring force is directly proportional to its change in length, which is equal to the displacement of the body from its mean position. According to Hooke's law, spring force F is directly proportional to its change in length, which is equal to the displacement x of the body from the mean position and acts in a direction opposite to the displacement. Thus, spring force F is proportional to minus x, or spring force F is equal to minus kx, where k is the spring constant, and the negative sign indicates the force is opposite to the direction of displacement. Let this expression be equation 1. spring force F is similar to the force discussed in the force law for simple harmonic motion. That is, F is equal to minus omega square m into x. Thus, we can say the spring mass system executes simple harmonic motion. Let this expression be equation 2. The spring constant K depends on the elastic properties of the spring. Its value is large for a stiff spring and less for a soft spring. The mass attached to the spring is m, and spring constant of the spring used is K. Comparing equations 1 and 2, we get omega square m is equal to K. On simplification, the angular frequency omega of the spring will be equal to under root K by m. The time period t of the body executing simple harmonic motion will be equal to 2 pi by omega, which will be equal to 2 pi into under root m by k. Let this be equation 3. Equation 3 is valid under the assumption that the spring itself is of negligible mass. This expression holds irrespective of whether the spring mass system executes oscillations in a horizontal or vertical direction. Now, consider a simple pendulum executing simple harmonic motion. A simple pendulum is a heavy point mass attached to a light inextensible string suspended from a rigid support. The length of the simple pendulum is L. The length from the point of suspension to the center of gravity of the bob is called the length of the simple pendulum. The bob shown has a mass m, and the simple pendulum executes oscillatory motion when slightly pulled aside by an angle theta and then released. When the simple pendulum is in the extreme position, the forces acting on the bob of the pendulum are its weight mg, which can be resolved into mg cos theta and mg sin theta. The component mg cos theta is along the string, and it is balanced by the tension in the string T1. The radial acceleration of the pendulum will be omega square L. Tangential acceleration will also be present since the motion of the bob along the arc of the circle is non-uniform. The tangential component of the weight of the bob, mg sin theta, acts towards the mean position and is known as the restoring force. Thus, the restoring force on the bob is equal to minus mg sin theta. The torque tau on the bob of the pendulum about the point of suspension is equal to minus L into mg sin theta, since the torque will be the product of the perpendicular distance from the point to the suspension of the bob into the force. Let this be equation 4. But the torque on the bob is also equal to I into alpha, where I is the moment of inertia of the system about the point of suspension, and alpha is the angular acceleration. Let this be equation 5. Equating 4 and 5, we see that I into alpha will be equal to minus mgl sin theta, or alpha will be equal to minus mgl sin theta by I. When the theta value is small and is expressed in radians, we can write sin theta equal to theta. Therefore, alpha will now be equal to minus mgl theta by I. We see that the angular acceleration alpha is proportional to the angular displacement theta, but in the opposite direction, which is the condition for simple harmonic motion. Hence, the simple pendulum executes angular simple harmonic motion. But in angular simple harmonic motion, angular acceleration alpha will be equal to minus omega square into theta. From the above equations, we get minus omega square into theta equal to minus mgl into theta by I. On further simplification, we get omega equal to under root mgl by I. Therefore, the time period of simple harmonic motion of the simple pendulum will be equal to 2 pi by omega. Substituting omega value, we have time period t equal to 2 pi into under root I by mgl. Since the moment of inertia of the system is equal to m into L square, we have the time period t of the pendulum as 2 pi into under root L by g. Thus, the time period of a simple pendulum executing small oscillations is directly proportional to the square root of the length of the pendulum and inversely proportional to the square root of the acceleration due to gravity. Seconds pendulum is a pendulum whose time period is equal to 2 seconds. Earlier, we discussed ideal simple harmonic motion where a body oscillates such that the amplitude does not decrease with time as there is no dissipation of its total mechanical energy. This takes place only in ideal simple harmonic motion. When a boy plays on a swing, there must be an external periodic force to maintain the constant amplitude of the swing. In the first case, the pendulum's amplitude decreases due to the opposing forces by the surrounding medium. It also decreases due to the non-ideal nature of the elements of the pendulum, such as the bob. We had considered the bob to be a point mass, which is not possible. Due to these reasons, the mechanical energy is dissipated while doing work against the resisting force. Hence, the amplitude of the oscillations decreases with time and the oscillations of the pendulum are known as damped oscillations. These forces that resist the oscillations of the pendulum are known as damping forces. Now, consider a mass attached to a spring held vertically. There is a slight elongation in the spring due to the mass attached to the spring. This elongated position is the equilibrium position of the mass. When the mass is pulled down slightly by a distance x from this equilibrium position and then released, it executes simple harmonic motion under the effect of the restoring force F equal to minus kx. Let this be equation 1. The spring then executes simple harmonic motion with an angular frequency omega equal to under root k by m and the time period of oscillation denoted by 2 pi under root m by k. Let this be equation 2 and 3 respectively. In the presence of damping forces, the angular frequency omega will be less than the value given in equation 2. There is a loss of the mechanical energy of the spring system, which appears as heat to the system and its surroundings. If the spring is immersed in a viscous liquid, the viscous drag on the system brings the mass to rest faster than when the surrounding medium is air. Mechanical energy is lost faster by the spring system in the viscous liquid. The damping force is generally proportional to the velocity of the mass executing simple harmonic motion and acts opposite to the direction of the velocity. The damping force F1 is equal to minus BV, where B is a constant called a damping constant, whose value depends on the surrounding medium's characteristics such as its viscosity, and other factors such as the size and shape of the block. Let this be equation 4. The SI unit of the damping constant is kilogram per second, and its CGS unit is gram per second. If the acceleration of the block at any instant of time t is a, then from Newton's second law of motion, we have the net force on the block m into a is equal to minus kx minus bv. Since we are discussing simple harmonic motion in one dimension, the net force on the block represents the sum of the restoring and damping forces. Since acceleration a is equal to d square x by dt square, we now have m into d square x by dt square equal to minus kx minus bv. This can be written as m into d square x by dt square plus kx plus bv equal to 0. As velocity can be expressed as dx by dt, we have the equation md square x by dt square plus bdx by dt plus kx is equal to 0. This is a second-degree differential equation in x and t. Let this be equation 5. The solution of the differential equation 5 is of the form x of t is equal to ae power minus bt by 2m into cos omega 1t plus phi, where a is the amplitude of oscillation and omega 1 is the new angular frequency under the action of the damping forces. Let this be equation 6. Here, omega 1 will be equal to k by m minus b square by 4m square whole under root. Let this be equation 7. We see that the motion of the block attached to the spring is not strictly periodic in nature, due to the exponential function in equation 6. This is because the value of the exponential function e power minus bt by 2m always decreases with time t. For small damping, that is, when the value of b is very small compared to under root k by m, we see that the amplitude of the approximate periodic motion of the spring system is ae power minus bt by 2m, and the amplitude gradually decreases with time. Now let us look at the energy of a harmonic oscillator. For a body executing ideal simple harmonic motion, we have total mechanical energy is equal to half Ka square, where A is the amplitude of the oscillations and K is the spring constant. For a body undergoing damped simple harmonic motion, we have the total energy equal to half Ka square into e power minus bt by m. This expression shows the dissipation of energy as the total mechanical energy of the oscillatory decreases with time t. The vibrations of a body can be of two types, namely free vibrations and forced vibrations. Resonance is a special type of forced vibrations. When a body is excited and released, the vibrations of the body are called free vibrations. The simple pendulum executes free vibrations. In the presence of damping forces, like viscous drag due to air, a body oscillates with decreasing amplitude and finally comes to rest. Earlier, we saw that when a child was playing on a swing, someone pushed the swing to maintain sustained oscillations, to overcome the damping forces. An external force is necessary to keep a pendulum oscillating in case damping forces are present. Let us assume that the external force is periodic in nature and has an angular frequency omega naught. The body starts vibrating with angular frequency omega naught instead of its own natural angular frequency omega. In this case, the oscillations of the body are called forced oscillations or driven oscillations. The external periodic frequency omega naught is also called driving frequency. Let us denote the time-dependent external periodic force f of t as f naught cos omega naught t, where f naught is the amplitude of the external periodic force and it is also time-dependent. From Newton's second law of motion, we know that the net force on a body executing forced oscillations, M, A, is the sum of the restoring force, damping force, and external periodic force. This is equal to minus kx minus bv plus f naught cos omega naught t. Since acceleration a is equal to d square x by dt square and velocity v is equal to dx by dt, we have md square x by dt square plus kx plus b into dx by dt, which will be equal to f naught cos omega naught t. Let this be equation 1. This is the second degree differential equation representing the periodic force of angular frequency omega naught applied on the mass m. The body is initially vibrating with its own natural frequency omega for a short period of time. But later, when we apply the external periodic force, the body oscillates with the frequency of the external periodic force, that is, omega naught. On solving the second degree differential equation, we get x of t is equal to a cos omega naught t plus phi, where x is the displacement under the influence of the external periodic force. Phi is the initial phase of the oscillator, and A is the amplitude of the forced oscillations. Based on the solution of the second-degree differential equation, we get the amplitude of the forced oscillations A is equal to F naught by the under root of m square into omega square minus omega naught square whole square plus omega naught square into b square, and tan phi is equal to minus v naught by omega naught into x naught, where m is the mass of the particle and v naught and x naught are equal to the initial velocity and initial displacement of the particle at time t equal to 0 respectively. Now, when the external periodic force is such that omega naught is very small compared to the natural frequency omega of the body, then value of omega naught into b is much smaller than the value of m into omega square minus omega naught square, and hence we can neglect that term in the expression for amplitude. Then, amplitude A will be equal to F naught by m into omega square minus omega naught square. Earlier, we learnt that an external periodic force is necessary to maintain sustained oscillations of a body executing oscillatory motion. Under the action of such external periodic forces, the displacement x of the body is expressed as x is equal to a cos omega naught into t plus phi, where x is the displacement under the influence of the external periodic force, phi is the initial phase of the oscillator, and a is the amplitude of the forced oscillations. The amplitude of the forced oscillations is expressed as a is equal to F naught by the under root of m square into omega square minus omega naught square whole square plus omega naught square into b square, where F naught is the amplitude of the external periodic force. Let this be equation 1. The value of phi can be calculated by the relationship tan phi is equal to minus v naught by omega naught into x naught, where m is the mass of the particle and v naught and x naught are equal to the initial velocity and initial displacement of the particle at time t equal to 0 respectively. Now, when the external periodic force is such that omega naught is very small compared to the natural frequency omega of the body, then the value of omega naught into b is much smaller than the value of m into omega square minus omega naught square, and hence we can neglect the term in the expression for amplitude. Then, amplitude A will be equal to F naught by m into omega square minus omega naught square. Let this be equation 2. Now let us examine the case when the value of the driving frequency omega naught is very close to the natural frequency omega of the body. Then in the expression for amplitude A, the term in equation 1, m square into omega square minus omega naught square whole square, becomes negligible compared to the value of omega naught square b square, and hence amplitude A becomes equal to F naught by omega naught b. Let this be equation 3. We see that amplitude A depends on the driving frequency omega naught, and also the damping constant B. The amplitude shown in equation 3 represents the maximum possible amplitude for the body under the effect of the driving force. Thus, we can see that there is an increase in amplitude of the body when the driving frequency is close to or equal to its natural frequency, and this phenomenon is called resonance. Let us look at some examples of resonance. As a first example, consider 3 pendulums A, B, and C supported by the same rubber cord. We see that A and B are of unequal lengths, but A and C are of equal lengths. Hence, A and B have different natural frequency of oscillations, whereas A and C have the same natural frequency. Now A alone is set into vibration mode. We can observe that B and C also start oscillating under the influence of A. That is, B and C execute forced oscillations under the influence of the external periodic force of A. We see that B oscillates with decreasing amplitude, but C starts oscillating with increasing amplitude. That is, C exhibits resonance since the driving frequency is equal to the natural frequency of C. The pendulum B executes forced vibrations, and its amplitude decreases due to damping. Even though damping occurs, C executes resonant vibrations. Let's move to the second example. A tuning fork of frequency F is excited and held near the open end of a cylindrical pipe held in water. Now, gradually, the pipe is lowered into the water in regular steps, and the excited tuning fork is held near the open end of the pipe. At a particular level of the water in the pipe, the air column present in the tube resonates to the frequency of the tuning fork, and a large booming sound is heard which indicates resonance. Let's move on to the next example. An earthquake, which is actually a seismic wave, causes maximum damage to those structures or buildings whose natural frequency of vibrations is close to the frequency of the seismic wave.